Welcome everybody to SD Access Troubleshooting the Fabric. My name is MichelPeters. I'm part of the SDA solution escalation team working for the BU. I'm living in the Netherlands. I started in Cisco in '99 and I've been working with the Catalyst just since then. I started off with the LAN switching tech in Cisco and then moved on to BU escalation. And I'm currently focusing on SD Access solutions within the BU. I'm based in Amsterdam, so you might not often get to speak to me, but sometimes you might. I've got 2 CCAs, and that's pretty much everything that was interesting about me. So let's talk about SD Access, which is much more interesting than what we're talking about me. The agenda for today will be, first we're going to cover the fabric. We're just going to have a quick introduction what the fabric is, just to make sure that we all understand it, and also the differences that we have inside of it between SD Access and the LISP technology. And how we're learning in the fabric, how endpoints are being discovered and being put into the fabric, and the last part, sending things through the fabric. There's going to be a lot of CLIs being used, of course. It's a troubleshooting session, and we're going to get onto the CLI. I tried to put them onto the slides as good as possible, but it's not always very easy to see it from a distance. So there's the PowerPoint presentation you can download via the Cisco Live app, so that's sometimes useful to just download it to be able to follow along. And also to keep that at home so that you can just review it and see the commands that we have been using. So to talk about the fabric, what is the fabric? As we have, the fabric itself is a technology, not per se, it's more a solution that we designed a couple of years ago. We took a few technologies we already had inside Cisco. We used the LISP control protocol to be able to build the fabric. We used the VXLAN protocol to be able to encapsulate traffic through the fabric. We use Cisco TrustSec to insert some micro-segmentation to be able to get a secure fabric. And we use IBNS, that's also already present on the switches, to be able to do authentication so that you could actually get your host assigned where you want to have them. So SD Access by itself is not a technology, but it uses these 4 technologies to be able to build a fabric. If you start troubleshooting SD Access, obviously it's important to know these 4 components. By knowing these 4 components, it's much easier to troubleshoot, especially from the end user perspective. IBNS is something that you often will have problems with. .1x, map authentication, ICE, things like that. And Cisco TrustSec for your micro-segmentation is also something that you might experience a lot with the endpoints. VXLAN data plane protocol, we don't have a lot of problems with. Typically, is quite reliable. It's just forwarding traffic from A to B. And the LISP control protocol, we do have a lot of issues with, but it's more complex to troubleshoot. And typically, if something's broken there, it ends up being a bug or something that's misconfigured. So how does the fabric work? We have a layer 3 core inside the fabric. We can deploy that either via LAN automation or you can manually configure it. We don't support layer 2 between the fabric components, only layer 3 because we need to avoid flooding of the VLANs for the downlinks, and that's why we just do the layer 3. The major component inside the fabric is the control plane node. The control plane node is basically the brains of the fabric. He knows where everybody is, he learns where everybody is, and he will direct the traffic through the fabric based upon the information he learned. He's not part of the forwarding plane, he's just knowing where everybody is and telling all of the components inside the fabric where they have to go. Of course, you also want to have endpoints inside the fabric. We connect them to the edge nodes or the edge node connectivity. We can connect PCs, APs, everything you want. Everything, if it's an endpoint and it's being connected, we connect them to the edge nodes. To get out of the fabric, we have border nodes. We have multiple types of border nodes. You have internal border nodes, external border nodes. And they provide the connectivity from your fabric to the outside world, either to the internet, to your data center, or to other fabrics. That's all connected via the border node functionality to be able to get to the outside. Behind the border node, we also have fusion devices. The fusion devices are typically not part of the fabric itself, but are quite important. The border node hands off via VRF light towards a fusion device. The fusion device can be a firewall, it can be a Cisco router, it can be any type of router. And that needs to stitch all the different virtual networks together to be able to connect everything to your data center or together, or if you don't want them connected, it's also possible to just leave them separated. The fabric devices can have multiple roles. Here I'm drawing them all separately, but in a lot of cases, the border node and the control plane node are being co-located. So you have one device both being a border node and being a control plane node. But you can also have the occurrences if you have a small site that you only want to put 1 stack or 2 stacks. Then you have a FIAP device, a fabric in a box, and that device can be both edge node, control plane node, and border node, but it can also run the WLC packets, so you can basically have the entire fabric on one box, and you can connect everything up there, and then via SD Access Transit, you can connect up to your main sites. So they can have multiple roles, but you can also separate them. It depends on the scale of your network, if you want to keep them separate or if you want to keep them apart. So that's the SDA fabric components. In Lisp, of course, we also have namings, and especially if you start troubleshooting in the CLI commands, you might be able to run into the CLI commands that we're using there. If you look at the outputs itself, we have an XTR, which is basically a combination of an ingress tunnel router and an egress tunnel router. Those are the components that basically take the fabric, or that take the traffic from the endpoints and put it onto the fabric, and take the traffic from the fabric and put it out to the normal PCs. They're responsible for registration and also for looking up the destination. So the XTRs basically are the edge nodes inside your fabric, and they provide endpoint connectivity. The map server, map resolver, that's the name for the control plane node that we have inside Lisp. So if you see any of the Lisp specifications that you can download from the RFCs, they won't talk about a control plane node. They will typically talk about a map server and a map resolver, and that's what we use, the control plane node inside SDA. The proxy XTR, that's the border node. It's not a normal XTR, but it's a proxy XTR because it provides connectivity outside the fabric, and that's why it's not typically called a proxy ETR. So that's the naming. Now, how do we actually build a fabric? Typically, you have a physical topology. All your switches connected, either the border nodes connect directly to the edge nodes, or there's an intermediate node in between, depending on the topology that you have. What you will have with SDXs is one stable underlay. We've only put the loopback interfaces advertised inside the underlay network, so your global routing table should be stable. Changes in the overlay will not impact the underlay network. What you then can do is create virtual overlay networks. 1, 2, 3, 4. They've been built on top of things. The underlay network will not change no matter if you add or remove any of the overlay networks. It's all being tunneled from loopback to loopback, so the underlay network will remain completely stable, and the overlay network is just being built, and you do the handoff on the border nodes towards your Fusion device. So to look at the Lisp basics, the basic from Lisp is basically that we decouple where you are inside the network, who you are. In traditional networking, where you are and who you are basically coupled together. You have an SVI on your access layer or your distribution layer, and below there you have all your clients. With SD Access, we don't have that, and with Lisp, what we do in SD Access is we decouple it, so every endpoint will be learned in an endpoint identifier space. We call that EIDs. And we also have routing locators, which are RLOCs, and those basically tell us where you're being located. So the combination of where you are is the RLOC, and who you are is the endpoint identifier. If you're roaming around the network, the only thing that we need to do inside the fabric, we update the RLOC from one IP address to the other IP address, and that means that the client roams from one destination to the other destination. So the routing locators are inside the network. That's typically the loopbacks, and the EID space, that's all your users, all your MAC addresses, all your IP routes, and everything there. So this is how it works. Basically, an EID gets learned. There's a PC, they come up, connected to an edge node. The edge node will detect that using device tracking or MAC address learning via the switches. Once it's being learned, we register that with the control plane node. That moment, the control plane node will know about that specific endpoint is behind this specific device, and it will make the combination to be able to get reachability there. Then the next time, of course, the client wants to send something. For example, the client on the one side wants to send something to the other side. He sends a packet. We send that to the CPU so that we need to resolve the destination. What the edge node then does is send a packet towards the control plane node, asking, I want to reach a specific IP address or a specific MAC address. Where is that located? The control plane node will just respond back saying, this specific IP address or MAC address is located behind this specific edge node. Once we have that information, we can build the map cache on the edge node, and using that map cache, we can then forward the traffic. What we then do is encapsulate it completely into VXLAN and forward it from one edge node to the other edge node. The other edge node receives the traffic. He knows where the other endpoint is because it's locally connected to him. He de-encapsulates the packet from VXLAN and sends it on to the endpoint. So that's a very basic overview of how Lisp works. It's very simplistically explained like this. There are, of course, more things going on, but in essence, this is the way that Lisp works. We just ask where is somebody located, and then we get a response back, and we just tunnel the traffic towards it. So for the data plane packets, we want to tunnel layer 2 and layer 3. Originally with LISP, they had an encapsulation method that only encapsulated the layer 3 packet, so it stripped out the layer 2 header. For SDAccess, we have support for both layer 2 and layer 3, so we started using VXLAN encapsulation. And with VXLAN encapsulation, we can just take the entire packet and we encapsulate that completely inside a VXLAN frame. So we create a new Ethernet header, new IP header. There's a VXLAN header, and inside the VXLAN header, we put in the LISP instance ID, and the LISP instance ID basically identifies inside the fabric which specific virtual network you're on, and if it's layer 2 or layer 3. And we also put in the secure group tag, which is used for CTS. Every packet inside the fabric will be tagged with its corresponding SGT tag. If you don't have any authentication or configuring of SGTs, it will just set it to 0, but every packet will be labeled inside the fabric saying this specific frame belongs to this specific SGT. The moment that it actually goes out of the fabric, then we do the enforcements with CTS. But throughout the entire fabric, that specific frame on ingress will have an SGT applied to it, and it will travel all through the fabric. So how this looks like on a packet capture. This is a packet capture for my lab. It's just a simple ping going back and forth. So you can see in the bottom there's an encapsulated packet. That's the layer 2 packet that originally was being received by the edge node. There's a new header that's being built to transport the packet from one edge node to the other edge node, a new layer 2 header, new layer 3 header, IP address from loopback 0 to loopback 0. And there's also the VXLAN header that contains our LISP instance ID that will tell us which overlay network this specific frame belongs to, and also the SGT, which is the secure group tag that we put into the group policy ID. So that's how packets will go through the fabric. This is a layer 2 frame, so you will actually see an encapsulated packet with a full layer 2 header. If you have a layer 3 frame going to the fabric, that will be a 4000 range LISP instance ID. We also put in a layer 2 header, but it will be more a mock header, so that won't actually have the destination and the source MAC address as you would get it out, because we only care about the IP frame, so there's some information in there internally for our switching, but you will just see a mock header being used for layer 3 frames. What's also important with SDA is the edge configuration. If you have running SDA, everything will be pushed by Catalyst Center. What we use with Catalyst Center and SDAccess is that we use an IP Anycast gateway. That means all the edge devices will use exactly the same IP address and exactly the same VLAN and exactly the same MAC addresses. This helps by scaling. If you have 100 edge devices that all have the specific IP pool, you only need one IP address, so that's already a benefit. But it also makes it simpler. We just put everything, if you roam from A to B, IP address is the same, MAC address is the same. The client can just move from A to B, and he doesn't have to change his ARP table or anything, because the uplink MAC address is exactly still the same. This is how that would look like if you look at one of the devices. This is one edge device. If you look at running interface VLAN 1021, which is one of the virtual networks, you can see a MAC address statically configured, an IP address being configured, and it's part of the VRF that's corresponding to the virtual network that's being defined on Catalyst Center. If you look at any of the other switches as well, it has exactly the same MAC address, it has the same VRF configuration, and it also has the same IP address configuration. In theory, if you look at all your edge devices inside your network, a lot of the config, especially for the downlinks, for all these user VLANs, it will be exactly the same, and you can just copy over one from the other if something missing. Catalyst Center obviously maintains that. He makes sure that everything is in sync. But basically, if you will look at it, if you see a mismatch between two edge devices that it has a different IP address or a different MAC address, there's definitely something wrong there, because they should be exactly the same. The problem that we're using the SVI or the Anycast IP address and a static MAC address is also that you have to be careful with layer 2 connection between switches. We use the same MAC address everywhere. If you connect the layer 2 switch in between, it's going to get confused. It doesn't know how to route traffic anymore, switch traffic, and it starts being a problem. That's why we're saying we only have layer 3 uplinks, not layer 2 uplinks, and you cannot connect edges directly. If you start trunking them there and you have flooding enabled in a network, in the fabric, you start creating loops, and that's really not something you want to have. So the best thing is make sure that you use layer 3. LAN automation really helps a lot with deploying layer 3. But layer 3, you have to be careful, and you also have to be careful with people connecting SFPs from one edge device to the other one. So that's the basic overview of the fabric. Now we're going to look at the part about troubleshooting, about the learning in the fabric. The control plane node is the brain, basically, of the entire fabric. It builds in a complete table, and in that table, it basically maintains what EID belongs to which instance ID and what the RLOC is that being associated with it. The control plane nodes, you can have multiple inside the fabric. If you have wireless, you can have up to 2 control plane nodes in the fabric. If you don't have wireless, you can have up to 8. Typically 8 is a bit excessive, but 2 is what minimum recommended is, because if one of them go down and you only have one, obviously you have a connectivity problem, and that means that nothing's connecting. So the tables on the control plane node are basically quite simple. It's just a tuple saying instance ID, RLOC, and the EID, which can be a MAC address, it can be an IPv4 address, or it can be an IPv6 address. We use different instance IDs for layer 2 connectivity and for layer 3 connectivity. The layer 3 connectivity typically starts with 4000, so it starts at 4097 upward. If you have layer 2, it basically starts with 8182 and then goes upward. Every VLAN or any cast that you configure on Catalyst Center will be a separate VLAN, so it will be a separate layer 2 instance. If you group them all together, we put them into a VRF and you have your virtual network. IPv4 and IPv6 share the same LISP instance ID, so they're actually the same, but it's just either an IPv4 or an IPv6 address. So that's the control plane node. If you want to look at entries, we have a command called show LISP instance ID, and then you can give the instance ID, or you can do a star. Then you can define the address family that you want to look at, IPv4, IPv6, or Ethernet. In this presentation, I'm just showing you everything with IPv4, but the outputs are exactly the same for Ethernet and for IPv6. It's just IPv4 is the one that's most commonly used. For these slides, that's the one I've been looking at. If you look at the information on the control plane node here, for one specific entry, you get much more information. You can also not include the IP address on the end, and you just get a quick overview of everything that the control plane node knows. But if you look at one specific entry, you get much more information being detailed. What's important to note there is basically the registration history. When was the specific EID first learned? That can give you a lot of information if you have troubleshooting. You know, the client had a problem 15 minutes ago, and the last registration was also 15 minutes ago. You know there was something wrong with registration. If you had 15 minutes ago a problem with a specific client and the client's been up and running for 1 week, that means that there was no re-registration, so the problem is not registration related, but it might be something else that has been going on for your specific issue. So it's very easy to check it. You have to use the specific IP address to get the complete overview of things. There are more information here as well. Proxy reply is one thing that we set inside SD access. Originally in LISP, we don't do proxy reply, and instead of the control plane node responding to a map request, it would forward it on to whoever registered that specific IP address. With the proxy bit, it means that the control plane node will respond directly, which makes troubleshooting much easier. You just have to take a packet capture if you want. Of the control plane node, you can see the map request going out, you see the map replies coming back, just to be able to confirm what's going on. The TTL by default is 1 day. That means an entry that's being registered inside the fabric has a lifetime of 1 day. After 1 day, it needs to either be refreshed or we'll just remove it from the fabric. That 1 day is also the thing that we use inside the map caches. A map cache has also a lifetime. Whenever an edge device builds a map cache, it will by default have a map cache lifetime of 1 day. You can tune that down. Normally that's not recommended or not needed because we do maintain all the tables, and if an IP address is being removed from the fabric, we'll deregister it. But especially environments where you have, for example, a convention center where you have a lot of registration coming on for people that are just shortly there, you could decrease it just to be able to clean up and make sure that your tables are not being overloaded by registrations of things that already left the fabric but just not have been detected. So this is the first part of the command. This is the continuation of the command, which will give us much more information regarding where that specific endpoint actually is being located. As you can see there, the first part says the ETR that's being registered. As before, I told you the edge node itself is an XTR, which is an ETR and an ITR. The ETR component is the part that's actually responsible for registering MAC addresses. In this case, the ETR that registered that specific IP address is this specific one. And at the bottom, you also see the locator information, and the locator information is the one where we're actually going to send the traffic through. And there you can also see the status is up, and the priority, and the wait for that, how much information is there. The locator and the ETR are typically the same, unless if you have wireless. And with wireless, the MAC addresses that you are learning are being registered by the WLC. And then the ETR will have the IP address of the WLC. But for normal wired clients, and for IPv4 and IPv6 addresses, the ETR is typically the device that's registering it, and it's also registering itself, saying, I am the locator, you can reach me behind it. But it's a very distinct difference between them. The ETR is just doing the registration, and the locator information is really how to reach towards the endpoint itself. You also have priority and wait. This is for an endpoint, so it's not very important. But for border nodes, we also have the ability to load balance traffic. So by default, everything has a similar priority. So if a route is being learned via 2-pass, we'll load balance traffic. We can also assign it a different priority. And if you assign it a different priority, that means that you will assign one border node to be the priority border node, and that will receive all the traffic. The other one will just be on standby in case that the first one fails, and then we start switching over. And then you will just see that one registration will be 10, and the other one might be 1, or something like that. This is, for example, a registration from a specific subnet that's being brought into the fabric from 2 different border nodes. If you just look at show LISP instance ID 4100 IPv server without specifying any IP address, you will just see that it's being registered who is the last register, but that doesn't give you the information that there are 2. That's why it's very important to not just look at the overview with show LISP instance ID IPv4 server, but also look further into the detail regarding that specific entry. Because in this case, if you just look at IPv4 server, you only see 1 border node. But if we look at the more detail by specifying the IP address, you can see that there are 2 ETRs that registered that specific IP address. That's both border nodes. The locators as well, they are both there saying border node 1 and border node 2. They both said, OK, I'm a locator, you can reach me there. We will load balance traffic between them because that's what the edge devices will do. But you have to be careful when you start troubleshooting it and you think, oh, why is my border node 1 not showing? It's just because the overview command without the IP address only shows the last registration, not the other one as well. And this way you can find them both and then be able to look at that. So how does the control plane node actually learn the information? The control plane node gets the information from all the edge devices. The edge devices learn everything via device tracking or MAC address learning. Once they actually learn something, either via device tracking or via MAC address learning, it has a LISP session from the edge device towards the control plane node, and it just sends a registration message saying, I am this ETR, this is my locator information, and I learned the specific endpoint in this specific instance ID. The edge nodes, they can have multiple control plane nodes because you have redundancy inside your fabric. The control plane nodes themselves do not synchronize amongst themselves. They connect only to the edge devices and the border nodes and learn the information from there. Even if one of the border nodes or the control plane nodes would power cycle, it just goes down, it comes back up, it gets the information back from the edge devices and rebuilds its entire table. So both control plane nodes should be in sync, but they don't synchronize amongst each other. There's no LISP session between the control plane nodes. They just operate completely separately and get the information from the edge devices and the border nodes all themselves. So to look at the show LISP sessions, there's the command show LISP session that will just give you an overview. If you have a co-located border node and a control plane node, what you typically see on your show LISP session is that there are 2 LISP sessions with its own IP address. I highlighted them here in blue. The control plane node and the border node functionality are both on the same box, but they don't connect internally. They just have a LISP session between them as well. So there's IP communication between the border node component and the control plane component, and that's why you see this LISP session. If you have also a WLC on that same device, you would see an extra IP session or a LISP session that's also being connected to its own IP address, and then you have 3 LISP sessions on the same box, all connected to itself. That's perfectly normal. Behind that, you also have the users. The users is not the number of users that are on the edge device. The users are something else that we will see in the next slide. If you look at the show list session on an edge device, you will typically see it just going to both the border control plane nodes, and the status should typically be up. There are some cases, especially in older releases, when there's nothing to register on a border node, for example. If you only have external connectivity via the default route, we have nothing to register inside the network. And if we don't have anything to register, we don't bring up the LISP session. So those border nodes typically had a LISP session that was down. And that's just because it had nothing to register, and it's an on-demand thing. It's only going to open a LISP session the moment it actually wants to register something. So that LISP session stayed out. We have a new feature now that actually starts registering them anyway. There's a dummy registration that just happened, and that just brings up the LISP session, regardless if there's anything to register, yes or no, which makes troubleshooting a lot easier. It's a TCP session, so the session is not being established. It could be due to TCP, there could be connectivity issue. And it's done for reliable registration. With TCP, we know that we can connect to the other side. We send a handshake there. That means we have full connectivity. The session not up, debug TCP will also sometimes help just to see why you cannot have a TCP session coming up. And we have one session per border node, control plane node. If you want to look at more detail regarding the LISP session, you can specify the IP address, and you have to specify VRF default. VRF default is the global routing table. The LISP session runs through the global routing table, and that's why you have to specify that specifically. If you specify that, you can see the information, what exactly is being done inside that LISP session. In this case, it's just a lot of users, and that's the users that we saw with the before slide. A user is an instance ID for which we have registration. So we have IPv4, IPv6, MAC address registrations, IPv4 registrations, IPv6 registrations. They all consider the user. So the instance ID is a user. No matter how many entries we actually use through that, it's still one user. If you see on a LISP session, if you do show LISP session on any of the border node, on any of the control plane nodes, and you see a device that only has one LISP session, that's the PubSub subscriber one. It doesn't do anything, and that means there's nothing else actually going to that LISP session. That's typically a sign that there is a key mismatch. We use a LISP key on the border nodes or on the control plane nodes and on the devices. That key needs to match. It's an authentication thing. If it doesn't match, you typically will see that only one user is being there. The TCP session obviously comes up, but the registrations would always fail. And then you just see show LISP session showing one, and then you just have a key mismatch, and you have to correct the key on the edge device or on the control plane node. But typically, correcting it on the edge device is easier than trying to connect it on the control plane node. And that's been specifically a lot of problems with the WLCs, especially in the past, when we moved from using a LISP key that was UCI, which was a generic key, to a per fabric randomly generated key. In the migration from UCI to that key, there were some issues with provisioning, and some devices did not get the right key, and they would end up with a key mismatch, and then you could just see that they had a LISP session with only one user. So virtual networks and LISP instances, we define virtual networks in Catalyst Center. Catalyst Center just makes up the name, and it creates a virtual network or a LISP instance ID for every VRF. It has one, and for any CAS gateway, it also creates one with any VLAN. If you do show IPVRF on one of the edge devices, you can typically very easily see what's being happening. It will give you a LISP 0.4100 interface in this case. That means that specific interface is the virtual interface for the fabric. It's using LISP instance ID 4100. There are some downlink VLANs, VLAN 1021. There's also a loopback interface in that specific VRF, and that's the one that we use for multicasting. And this output was multicasting enabled on that specific VRF, and you will also see that. If you then look at the LISP configuration, this is for layer 3. You can see a configuration of some dynamic EIDs. The dynamic EIDs are the range of IP addresses that we will allow to learn inside that LISP instance ID. If there's a different IP address coming up, then it's inside the dynamic EIDs. It will be learned by device tracking, but LISP will just not learn about it because it says it's not part of a dynamic EID. And if it's not part of a dynamic EID, I'm not interested in it, I'm dropping it. You specifically see that very easily with IPv6. In this case, you have a database mapping for the global IPv6 address, 2001 DBA. If a linked local address would come up inside the fabric, which all the clients will have, like FE80, it's not part of the dynamic EID range. It will not be registered in the fabric. You can have layer 2 connectivity inside an IP pool, but of course, linked local IP addresses are not routable and thus not being routed, or not being registered with the layer 3 instance ID. Under service IP4, we also do the EID table VRF VN1, and that links that specific instance ID of 4100 or 499, which is a typo in the slides, towards EID table VRF VN1. There's also a database mapping command, and that one is the one that actually maps the loopback 4099 towards the fabric. It doesn't get dynamically learned. We just do a database mapping saying this specific IP address, we want to learn it into the fabric, and that means that we can start registering it. Behind there you see locator set, RLOC, and then a very long number. The long number is being made up by Catalyst Center as the UUID, but the locator set basically defines within SD access saying, okay, we want to connect everything using loopback 0. By default, iOS devices take the closest interface, but obviously for troubleshooting, it's much easier if we use the loopback 0 interface. So that's being defined under the locator set, and the locator set is being applied here as well towards these dynamic EIDs. And that's the information we register with towards the control plane node. Good, that's the information on the control plane nodes. Obviously, we also need something on the local side of things. The edge nodes themselves, they also build a small database. The control plane node has a full database of the entire fabric. Every edge node and every fabric device, border device, creates a database as well, but it's only a database, but it's local information. And whatever it learns inside this local database, it will register with the control plane node, and the control plane node will have the entire overview of the entire topology. So if you want to look at the local database, there's the command show LISP instance ID. You give the LISP instance ID, IPv4, or as I said before, IPv6, Ethernet, whichever you want to look at, and then database. You can just look at database, so you get all the overview, but you can also specify one specific endpoint you want to look at, and then you get the information from that one specific endpoint. In this case, I'm looking at one of the subnets from my lab. It's a /24 that I want to look at inside the database. It's on my border node, and I want to see what's really happening with that. There I can see for that specific entry, because it's also being learned somewhere else, that there are actually 2 locators for this specific one. I got my own one, which is my self-configured interface. That is mine. But there's also the other border node, and that's the one that's being tagged with auto-discovery. It's on the other side. We don't use it, obviously, because traffic routed towards here. We send it directly, but we know about it so that we know, okay, we're not the only one actually routing towards this subnet. There's also somebody else. You also have the information regarding in that output regarding the VRF. It's just easy to see where you're looking at, and the information there as well that is being learned through route import. And that's a good indication inside the database. How did we actually learn the specific IP address, MAC address, or IPv6 address? In this case, route import, which is on the border node, the fact that we just have BGP running there. We learned the IP address from the lab backbone via BGP, and we import it into LISP, and then it ends up with a database and gets registered with the control plane node. It's also important that the ACK field is yes. We use, as I said, LISP session, which is reliable transport. With the old original LISP implementation, it was UDP based. It was basically fire and forget. You send a registration. You don't know if it actually got to the control plane node. You didn't really care. You just assumed it's going to be there. If not, it's somebody else's problem. With SDA, we do reliable transport. We send it to the control plane node, and the control plane node will act back saying, okay, I got your registration. I acknowledged it, so it's being learned, and it's also reliable inside the fabric. So it's very important, especially if you look at the border node and you're importing a lot of routes, make sure that they're all being acked. If not, there might be a problem with the LISP session between the border node, or something else might be going wrong that's preventing the registration of that specific map server. So this is for 2 entries. Obviously, you can also look at it for 1 entry, but then you just have the similar output, but you just have 1 line. It also shows the border priority. In this case, you can also see here already, if I'm border node, if it's load balancing, or we both load balancing, or is the other one the priority or am I the priority? And you can configure that using Catalyst Center. There's a field that you can set priority for one of the two borders, and that will reflect in this specific field. You can also manually modify it, but that's not recommended with an SD access. But that's the way that you can see that it starts doing that. So this is also locally learned IP address. This is just a host route that's being learned on the system through device tracking. So it's a /32, it's a host route. It's being also advertised towards the control plane node, but instead of seeing it's being learned through route import, you can see here it's part of the dynamic EID range that we saw before in the configuration. The IP address should match, it should be part of that. If it's not, obviously we don't register it, but that way we can see, okay, this is just an IP address, it's being learned on the switch. Device tracking learned about it. Device tracking handed it over to LISP saying, I learned about IP address .8, and then we registered with the control plane node. And the same thing here, we send it to both control plane nodes, and they should be both sending in ACBAC saying, okay, I got the information, I learned about it, and it should be in my database as well. We learn the information through device tracking, so it's from R packets, DHCP snooping, RA frames, neighbor discovery for IPv6, or just macOS learning. Not macOS is learning, it's just normal on the switches. And then there's no dynamic EID range because every macOS should be able to be learned because there's no macOS ranges that you can define. There's also the SVI IP address, because that's also part of the dynamic EID range. It's also inside device tracking. So theoretically, it could also get learned into LISP, which it does, but it's not supposed to be registered with the control plane node. If we start registering the IP address of the SVI with the control plane node, that means all the edge devices, they all start registering the same IP address and the same MAC addresses. On border nodes, we allow multiple devices to register the same MAC address and IP address, but we don't do that for edge devices. There's no auto-discover, because we just assume if one IP address is learned from A to B, that either roamed or somebody tried to steal the IP address, because an IP address can only be on one edge device. If we would do that with the SVI IP address, you have 100 devices all registering that IP address with the control plane node. The control plane node would just send notifications out saying, well, you registered it, you send it to all the other 99, he registered it as well, and then they start coming back up, and you just have a lot of high CPU due to control plane traffic going back and forth just to be able to register the IP address of the SVI. To prevent that, we have the do not register bit, so that prevents the registration of the IP address of the SVI with the control plane node. So on the control plane node, you will see all the entries except the MAC address and the IP address of the SVIs. And you don't need that anyway because all the connectivity should be local, should not be reachable towards the fabric to get to the SVI IP address, because every device in the fabric will have it. The edge nodes will have an SVI IP addresses, and the border nodes will have the same IP addresses as loopback as well. So everybody knows about it, so there's no point in actually registering it anyway with the control plane node because we all know about it. There's also registration history. The registration history can help a lot if you have a specific problem just to see what happened around that time. There's a limited amount of registration history, of course, that we can have. The devices don't have a lot of memory, so we have a limited amount of memory that we can maintain them. But if you had a problem recently, you can just do the show LISP command with server registration history. Here I'm just using the last 10 and even had to cut them out, but you can just look at what was really happening. It depends on how big your network is, of course. If you have a university where all the students just happen to have a break and start moving around, you'll overload the entire registration history really fast. But if you have a normal enterprise environment where not everybody's having lunch at that time and just sitting close, then the registration history can give you some information, what's going on, who's moving, did it get registered, did it get deregistered, did it go from A to B, which can help you with troubleshooting just because you might see, okay, we had a problem around this time. The registration history is also showing that IP address moved from A to B or to C, and that means that there is a specific problem. The client's either roaming, which for wired, you don't typically see them roaming, but it can also be for wireless, and you do see wireless roaming as well to the registration history as well. But then the WLC bit is set to yes and the roaming might be set to yes as well. So it's a very useful command, but it's also limited in the amount of entries that you might be able to get over time. The next problem we have with the fabric with overlay networks is ARP resolution and deresolution for IPv6. The fabric itself natively does not allow flooding of traffic. It's all unicast tunnels that are going between RLOC to RLOC. That's great for communication, but for ARP it's a problem because an ARP is a broadcast, an IPv6 ND package, they're multicast. To be able to resolve that without doing multicasting inside the fabric, we learn all the address resolution information on the edge devices. So device tracking, as I said, it's running on all the edge devices. It's learning your IPv6 address, it's learning your IPv4 address, and the MAC address associated with it, and it's registering it with a control plane node. So the control plane node will have a complete overview of the entire fabric as well in the layer 2 instance IDs, which IP addresses are present, IPv4, IPv6, and the MAC addresses as well. Different from the IPv4 registrations, we learn every IP address. We learn regardless if it's in a dynamic EID or not. Here you can see even the FAO, the link local IPv6 address is being learned, because there can be communication inside an IP pool between link local addresses, so that should be allowed as well. What we then do with that information, if we want to send an R packet or resolve an R packet whenever it comes in on an edge device, we give that information towards LISP. LISP will query the control plane node saying, I need the address resolution information for IP address .2, for example. We will get a response back from the control plane node if he knows about it, saying the address resolution information for that one is this specific MAC address. What device tracking then does, he knows the destination MAC address, so he takes the broadcast destination MAC address or the multicast destination address from IPv6 and just rewrites it with the unicast MAC address, and then he can forward it to the fabric. It gets to the other side. When it gets to the other side, he can ARP back, or if he does ARP learning from it, he can just send packets back. But that way we can actually send through the fabric without actually doing broadcasting or multicasting, by just rewriting the destination MAC address. That works well for most of the devices. There are some IoT devices that are very stubborn. If it's not a broadcast or a multicast, they will not respond to an ARP packet. So in that case, you do need to start enabling flooding or get the vendor of the IoT devices to change that behavior, which typically easier to just enable flooding. Because if we do start flooding inside the fabric, we just flood the ARP and the ND packets instead of trying to rewrite them from multicast towards unicast. So that's something that you might see if you have communication inside the fabric from A to B. It's typically IP phones, IoT devices, things like that, that might not communicate on IPv4 or layer, but they might just connect MAC to MAC. And of course, we also do it IPv6 and things like that. This is how it looks like on the edge device itself. Here you can see the show device tracking database, just looking at one specific MAC address. Device tracking learned those specific IPv4 and IPv6 addresses. And as we said, we put everything into the database, and then it's being registered with the control plane node. So if you start troubleshooting ARP connectivity issues between two endpoints, it's always good to first check on your local database, make sure that you actually learn it first in the device tracking, because if device tracking doesn't know about it, it cannot tell LISP about it. And then if LISP knows about it, it should be registering it with the control plane node, and then the other side should be able to resolve it. We register it inside the layer 2 instance ID, not inside the layer 3 instance ID, because it's only for layer 2 communication, it's not for pure layer 3 communication. So that's what's associated with the VLAN information. So to resolve it, whenever we get an ARP packet or an ARP request sent from a specific endpoint to a destination, device tracking snoops it, it pushes to the CPU, and then we try to resolve it via LISP. What you will see in the show device tracking database, the moment that we start resolving it, you will see a MAC address there that's called FD. It's just a dummy MAC address that basically just indicates we're in the process of resolving it. It's being learned via API. It's not via DHCP or ARP. It's just a resolution that we're trying to do via LISP. The interface that's being tag is sometimes useful to see because that's the one that's actually requesting that specific IP address. So the ARP that triggered this specific lookup came from interface gig 1015. And then you also see the other ones there on the third line. That one has been resolved, and the moment that it's been resolved, we can rewrite the ARP packets towards the other side. Then you see the interface layer to LISP, and you see the link layer address, which is the information that we learned through the control plane node, and that's what we use to rewrite the destination MAC address. Packets towards that one, for ARP at least, we'll rewrite with that destination MAC address and then send them over the fabric as unicast. The lifetime of these entries are quite slim. We don't keep them in there for a very long time because ARP typically you ARP once and then you keep it in there for a long time. So it's like a few minutes and then device tracking removes it again. But if you have problems resolving ARP, it's always good to look at device tracking database first just to see if it's being resolved, yes or no. And if you see the entry there, it's not at the moment. You are just pinged an IP address that doesn't exist, and the IP address that doesn't exist, we send out a request. Obviously, it takes a longer time to get back because nobody is telling me where that specific MAC address is. So it's very useful. Of course, if you don't want to have ARP ND being rewritten, you can enable multicasting, but that you can, flooding inside the fabric, and that uses multicasting to be able to send the traffic to all the edge devices. But this is the default behavior for everything to communicate together. Sending through the fabric, of course, you don't want to just learn the fabric, you also want to send traffic through it, because in the end, that's what people want to do. Routing and switching through the fabric, the lookups that we do are exactly the same as you would have any Catalyst switch. So if the destination MAC address matches its DSVI MAC address, we'll try to route the frame. If the destination MAC address is any other MAC address than our own, we'll try to layer 2 switch it. So that's the routing decision or the switching decision that we make. It's purely based upon the MAC address. If it's ours, we'll try to route it. If it's not, we'll try to switch it. For routing, we use, like any other device, the longest match. So if you have a /32, that's a host route, that will be hit. If anything above that, you have the default route, it's a /0. So the longest match hit for a specific IP address is the one that we'll use to forward the traffic, similar like any other routing device. Once we actually hit something, there can be a few possible options that we'll actually hit with in SD access. The first one is forwarded. That means we have the information available inside a map cache to how to forward traffic from A to B. Then we can just encapsulate the packet, send it to the other side, and it gets to the destination, and the connectivity is being established. If we don't know about the entry yet, we need to resolve the map cache entry, and that's typically the signal or the signal plus forward. The difference between signal and signal plus forward is that signal just sends the packet towards the CPU and drops the packet. He doesn't try to forward it anymore. He just waits for the resolution and the next packet. The signaling goes to the CPU. The CPU just says, okay, I need to resolve this specific IP address. He sends it to the control plane node. He waits for a response, and he builds the map cache. With signal plus forward, we do about the same thing. We send it to the control plane node saying, I need to resolve this specific IP address. But at the same time, we also forward the packet towards the border nodes. The border nodes typically inside the fabric know where everything's located, or at least they know more than we might. We send it to the border node. If the border node does know the destination, he will already send the packet. If the border node doesn't know the destination, obviously we still need to drop it there. So that's the difference between signal and forward. And signal, most of our iOS devices these days, they support signal plus forward. A few releases back on the SVL pairs, we only had signal, but these days we can do signal plus forward on almost all Cat9 cases. We also have drop. Obviously, if we don't know how to forward a specific packet and there's no default gateway configured like a proxy ETR, we just try to forward it natively. If we don't know how to forward the packet, we'll just drop the packet. It's the same thing for layer 2 forwarding. If the destination MAC address is unknown and we don't have layer 2 flooding enabled, we'll just drop the packet because we don't know how to forward the packet itself. The map caches are built using the ECMP packets, encapsulated map requests. So we send them to the control plane node just to ask, okay, I have this specific IP address, where is it located? And that will trigger a map request, a map reply, and the map reply will come back to the edge node, and then we can build our map cache from it. So to look at the map caches itself, you can use the command show LISP instance ID. And the instance ID, like before, address family and map cache. This is just a quick overview of what you might see if you look at it. This is from my lab. There are a few actions. The static set map request that basically triggers the signal. Map reply forward native, that is an entry that's already been built. We got a negative map reply because the control plane node didn't know how to forward it. And it says forward native. That means try to forward it any other way because I don't know how to get the packet there. And then there's also complete entry, and the complete entry is just encapsulating it and getting to the other side. We'll look at those entries a bit more in detail. The first, how exactly the send map request works. We configure by default on all the edge devices and on internal border the map cache 000/0 map request. That basically means if you ever get an IP address that you need to resolve that you don't know about yet, just send a map request entry towards the control plane node and try to resolve it. On internal borders, obviously you don't want to do that. Internal borders, you only want to look up things that are actually inside the fabric. You don't want to just look up everything inside the fabric because you might get a response back and you want to route internal, not external. So what we typically do, once we hit a specific send map request entry, we send it to the control plane node. The control plane node will respond back with a map reply. Either it knows the information or it doesn't, and using that information we'll build the map cache, and the map cache will be used for forwarding the traffic. The negative map replies, they are quite interesting sometimes. What we do with the control plane nodes, if you get a map reply coming or get a map request for a specific IP address, we don't just respond back saying, I don't know where this specific IP address is. What the control plane node will do is just say, I don't know where this one IP address is located, but it gives the entire block of IP addresses that it doesn't know where this specific IP address belongs to. In this case, we tried to resolve 8888, the Google DNS. It doesn't know 8888, but it just told me, okay, I don't know 8.000/0. That means the entire 8, 9, 10, 11, it doesn't know about, it doesn't need to send any responses for that. It's a CPU protection mechanism. We don't need to send a map request and map reply for everything. It just sends the entire block saying, okay, if you're going to ask anything else, you don't have to because this is what I don't know about. So you can stop asking me. The lifetime of a negative map reply is typically 15 minutes. It's much shorter than the 1 day, of course, because things might change in the network. It might learn something. It might not learn something. But at least there's 15 minutes that you don't have to send anything for 8.000/7. And you will see it in your switches. So if you do show IPsec, you see sometimes routes that you might not expect, but it might typically just be the negative map reply that comes back in, and it just gets pushed into the Ceph tables itself. And if you get that, we have a few options. We can either, with LISP 1.0, we have static configuration for proxy ETRs for the external borders. There's a use PETR command configured. If that's configured and they're reachable inside the underlay network, we'll just forward the traffic there. With LISP 2.0, with SDA pops up, we have the dynamic default border, and that's basically advertising a border that says, I am an exit point, I know where the internet is located, and then you will see what you see there. It got a map reply back, it doesn't know how to reach there, but you can reach it through the unknown EID forward, and that just means all the traffic that you don't know how to send to the network, just send it to me and I'll take care of it. And that's the dynamic default border that you have with SDA 2.0. So those are the three options if you don't have use PETR or you don't have an active border node that has the default route with SDA 2.0. We'll just do forward native. That means look at the routing table, see if you can find another path. If you can't, just drop it. Or we can use the use PETR, or we can use the dynamic default border. The disadvantage when using the proxy ETR with the SDA 1.0 LISP BGP is that it's a static configuration. We just try to reach the IP address. We don't know if that specific IP address also can reach the network itself. So sometimes you can have a problem that a specific border node loses its uplink, but if it still advertises itself as a reachability, we just send traffic to it, and then you have black holing inside the fabric. What some people do, they just create an EM script. If the the route to a 000 gets lost, you can use that with an EM script. It just shuts down the loopback 0 interface. Loopback 0 interface gets shut down. The edge device is disappearing from the routing table, and it will stop using it for the use PETR. But the dynamic default border takes care of that, and we only advertise then reachability outside the fabric if we actually have the default gateway learned on a specific fabric device. This is how to encapsulate. Obviously, that's the thing that you want mostly. There's a resolution being happening, and then we get the information, in this case, for a specific subnet inside the network. We learned about it. It gives us 2 locators. That's because we have 2 border nodes for this specific one. They both have the same priority. That means on the overlay network, we'll start load balancing our traffic between those 2 devices. We either send it to RLOC1 or to the RLOC2. Depending on the flow, we use flow-based hashing inside the Catalyst 9000, so it's either going to either one of them. There's an extra layer of load balancing also going on underneath it. If you have dual uplinks, for example, and you try to reach one of those specific IP addresses, they might be able to be reached through A or through B. And we also load balance underneath there. So you do have a lot of load balancing going on, and you have to make sure as well that your load balancing algorithm inside your fabric, if it's complex, that it's not just taking the IP addresses as a hash, but it also takes care of the UDP port numbers. Within SDA, we start modifying the source UDP port that we use for all the traffic, and that can do the anti-polarization that not all the paths take the same path outside the fabric, because the UDP source port number changes by different flows that we use inside SDA. You can have load balancing to the network using that one. One thing, if you look at the show IP routing table as well, you have to be careful that if you look on an edge device, you do show IP route, you typically don't see anything. For the people that are just starting with SDA, they just do show IP route and they think nothing's working. The problem with LISP is that it doesn't talk to the routing table, it doesn't talk to the routing process, it just talks to Ceph directly. So in this case, you can see here as well, I'm looking at one specific route. It's not on the routing table, the default route is not there. It looks like there's nothing there, but connectivity is still achieved. The only thing that this one shows is our locally connected subnet, and it contains all the local attached hosts because LISP pushed them in there, but nothing from the remotes. But if you look at the Ceph tables with the show IP Ceph command, you do see all the information that you need, and that one does show you, this is the next hop, these are the locators that we need to use to reach it, and we encapsulate it using LISP 0.4100. That means we encapsulate it in VXLAN, and we use the LISP instance ID 4100 to get to the remote side. If you want to then look at which physical interface you need to take, you can either use the internal keyword. The internal keyword gives much more information from Ceph, and it will also include the physical interface, or you just do show IP route or show IP Ceph for the locator itself to be able to get to the other side. So for layer 2 forwarding, it's a bit different, of course. You still have the map caches. The map cache commands are exactly the same thing, but then it shows a MAC address and a VLAN instead of it shows an IP address and a VRF number. If you look at the MAC address table, they typically be referenced as CP learn. We learn some control plane node, and the interface will be layer 2 LISP for all the remotes one. By default, we don't flood traffic, but you can configure flooding inside the fabric to be able to get to the other side. So that's how you can recognize them. If you see L2 LISP, it's a remote one, and the map caches, it will just show the information. For layer 2 flooding, if you do enable that, you can define a multicast group as well, and that multicast group is being used to send traffic to, encapsulate it again in VXLAN with the layer 2 LISP instance ID, and the idea is that all the edge devices and all the border nodes in your fabric join to that specific IP address. So whatever packet's being sent by this specific edge node, everybody receives it. It will de-encapsulate the packet again, and then we can do flooding like that. The configuration will change then. You see there the broadcast underlay. That's the IP address that we will use for flooding the traffic. Flood ARP and D indicates that we stop doing the resolution from ARP, as we said before, and rewriting it. We just flood it to the multicast group, and flood a non-unicast that enables that we flood all the packets that we don't know about. For troubleshooting, you just typically, very important to look at your IPM routes. you look at your own loopback 0, you need to make sure that we actually have an egress interface. And if you look at all the other ones, you should typically see all the other edges in your mRoute table because everybody is sending some traffic and should be receiving traffic. The ingress interface for our encapsulating entry is typically null 0 because it's coming virtually into the fabric. We generate these frames. And on egress, you will see there the output interfaces are the layer 2 LISP instance ID 8188 and 8189. That means if we receive traffic through that specific multicast group, which is VXLAN, and it is part of those specific layer 2 instances, we'll try to de-encapsulate them and flood them towards our downlink ports. If you want to look at the multicast hardware program, or the unicast hardware programming for Mac OSs, there's the command that we can use on the FAT layer, the show platform software FAT command. It will tell us the information, all the LISP IP addresses, they are being sent with a type 0x1,000,000 and then 2 for dynamic. And at the destination port, you will see the RLOC that we use to be able to reach them. We don't typically need to troubleshoot on that layer. The forwarding in the hardware is typically quite okay. Most problems that we have is merely looking at the map caches and things like that. Here's some resolutions for troubleshooting, some tips that you can take at home. Just take a look at it. Very important, try these commands at home. Make sure that you actually understand what you can expect, because if you start troubleshooting, when you have a problem, you don't know what to expect. You don't know if it's right, wrong, or not. So it's very good to try it. Just make sure that you understand what you can expect, and then you should hopefully not have a lot of problems, but if you do, you should be able, hopefully, to be able to troubleshoot them. Thank you very much for your time. Please do fill out the session evaluation. And thank you very much.